This video will review essential concepts in thermodynamics as it applies to biological systems. Thermodynamics is all about the energetic driving forces that allow reactions to happen. Everything that happens in the cell, from cellular respiration to protein synthesis to enzyme-substrate reactions, requires energy. We will first review the three laws of thermodynamics. These laws help define fundamental quantities needed to study the energetics of reactions. The first law says that energy can neither be created nor destroyed, but can be converted between different forms. The first law is an observation of the universe and is often summarized as the law of conservation of energy. In other words, the total energy of a system, which is the sum of the different types of energy in the system, is constant. Before we move on to the second law, we must first review the concept of entropy. Entropy is essentially a measure of the amount of disorder or randomness in a system. You can think of a messy room as being a high entropy system, and a clean, orderly room as being a low entropy system. High entropy systems correspond to low energy, much like how laziness results in messy rooms. Low entropy systems correspond to high energy, much like how neat rooms require energy to upkeep. The second law states that for any process, the entropy of the system and its surroundings increases until the system reaches equilibrium. The second law says that the entropy of a system will increase until it reaches the final resting state. Much like most college dorms will get messier and messier until they can't get any worse. A restatement of the second law is that there is a universal tendency towards high entropy and low energy states. The third law states that a perfect crystal has no entropy at absolute zero. This law is simply a definition, but it makes sense intuitively. At absolute zero, there is absolutely no thermal energy. No movement is possible. So, there can be no randomness because everything is frozen still. A result of the third law is that entropy is always positive. Entropy can also be expressed quantitatively. In this equation, entropy is a function of the Boltzmann constant and the number of possible arrangements of the molecules in the system. The greater the number of arrangements, the greater the value of W, and the greater the entropy. This makes sense because the large number of possible molecular arrangements allows for a lot of randomness in molecule placement, and remember that entropy is randomness. The second equation expresses entropy in terms of the total number of states in the system and the probability of being in each state. Examples of states could be different levels of energy for the molecules in the system, and the PIs would be the probability for a molecule to be at a particular energy level. In general, entropy is highest if all states have equal probability. In other words, if there is a uniform distribution of probability. Gibbs free energy is the quantity that determines whether a reaction can occur without external energy input, or spontaneously. Gibbs free energy is a function of enthalpy, absolute temperature in Kelvin, and the change in entropy during a reaction. When the change in Gibbs free energy, delta G, is negative, a reaction will occur spontaneously. Why does this make sense given what we know about thermodynamics? Just by looking at the signs in the equation, we can tell that delta G is guaranteed to be negative when delta H is negative and delta S is positive. When delta H is negative, the reaction has released energy and is exothermic, which is energetically favorable. When delta H is positive, the reaction had to take in heat from the surroundings, which is energetically unfavorable. From the second law of thermodynamics, an increase in entropy, or a positive delta S, is favored, while a decrease in entropy is unfavorable. Notice that a spontaneous reaction is not necessarily fast. Iron exposed to air always rusts eventually because the reaction is spontaneous, but it happens over a long period of time. Our last major topic is equilibrium thermodynamics. When delta G equals 0, the system is at equilibrium. For a generic reaction of this form, the equilibrium constant KEQ is defined as in this equation. The brackets indicate concentration, and the EQ indicates the concentration at equilibrium. The standard Gibbs free energy, delta G naught, is the change in free energy that occurs when you start with 1 mole of each of the reactants A and B. It is related to the gas constant R, absolute temperature, and the equilibrium constant. We can rearrange this equation to get the equilibrium constant in terms of delta G naught. Finally, we can relate the non-standard Gibbs free energy, delta G, which we talked about earlier, to the standard Gibbs free energy. Note that in this equation, the term inside the natural logarithm is not the equilibrium constant because the concentrations represented by the bracketed terms are not concentrations at equilibrium. They are concentrations at some instant in the process of attaining equilibrium. Reactions with positive delta G naught values can still be spontaneous if the second term in this last equation is negative enough to make delta G negative. For this to happen, the concentrations of reactants must be much greater than the concentrations of products.